Hello, I welcome you all in this course on mechanical measurement systems. Today we shall discuss about the generalized model of a measuring system. Topics to be covered in this lecture are dynamic inputs, dynamic system response, generalized mathematical model of a measuring system, and operational transfer functions. Now we will start with dynamic characteristics of a measuring instrument. So far we have discussed the static characteristics. This we have amply discussed. In the static characteristics there was no function of time, right? But now we are going to discuss the dynamic characteristics of the system. Dynamic characteristics means the response of the system as a function of time. For example, I will give you an example. We take a voltmeter. Let us start with the voltmeter. When voltmeter is connected to the line, immediately it will give certain output. But you must have noticed the needle starting from 0 to a particular output takes some time. That is a dynamic response of the instrument. And you must have also observed in some of the machines or some of the voltmeters, the response of this needle is very sluggish. Slowly it will move from 0 and will be stabilized at a certain value. Second type of response is, this is a sluggish response. Second type of response is, the needle will move and it will overshoot the input and it will start oscillating. And after a certain time it will be damped and it will indicate a certain value. Right? So it takes certain time to stabilize. So that is also not very good. Very good dynamic response of the instrument. Third type of response you must have noticed that the moment you give input, there is no output, there is a time lag, and all of a sudden there is a movement in the needle. So you can have variety of outputs, variety of responses of the system for a given input. The input may be constant, input may be time variant. So there are certain terms which we have to understand before going through the dynamic study of the dynamic characteristics of the measuring instrument. The first is periodic signal. So dynamic input can be of many forms, as I said earlier. It can be periodic. Now periodic input means cycle is repeating itself. I mean after a certain time interval the cycle is repeated. For example, a rotating table or rotating disc. It is a periodic motion. It is not a simple harmonic motion or a harmonic motion. Harmonic motion is a kind of periodic motion where restoring force is proportional to displacement, or yes, is proportional to displacement. So that type of motion is known as harmonic motion, and a very good example of simple harmonic motion is the pendulum. Because when the pendulum is moving in this direction, restoring force is working in this direction. When the pendulum is moving in this direction, the restoring force is working in this direction. Another example can be spring. If you compress the spring, a spring will push the weight, right? Or restoring force will be proportional to the displacement in the instrument. Now, third type of input can be transient. Transient input. So transient input is the input for a very short time. It is non-cyclic, right? And it lasts for a very short time. So transient input may be like this. After a certain time interval, it will die out. For example, in the area of mechanical engineering, like quenching of steel rod, when you are putting high temperature steel rod in water, then input temperature variation is stabilized after a certain time and it becomes almost equal to the temperature of the media. That is the one sort of transient input, right? And third one is random input. So the last one, this is the last one, fourth one, it is random input. So as it is implicit from the name itself, it can vary with time. It can have any amplitude or no definite amplitude or frequency, right? The input is completely random. So random input is also one kind of input which can be considered. It may be continuous also. Random input may not die out with time, but certainly random input is not a cyclic input. It is not a cyclic input. So these are the certain type of inputs we have in dynamic systems, and there are certain more definitions like speed of response. So speed of response means, as it is clear from the name itself, it is the rapidity with which the system responds to the input, change in input. There is a change. So I gave you an example of voltmeter. Suppose there is a change in voltmeter 0 to 100 volt. How fast the output or the needle is moving and coming to the 200 volts is the speed of the response of the instrument. Then measuring lag, delay in response. Then another one is measuring lag. So many of these terms are clear from their name itself. For example, measuring lag. Suppose at time t is equal to 0, I give the input, and exact measurement I am getting at t is equal to delta t. So delta t is measuring lag. And measuring lag, again, I have already explained, it can be of two types. Retardation type, when needle is slowly moving and attaining the value. And another one is time lag delay. Time lag means initially there is no deflection, but all of a sudden the needle will come to the output, right? So there are certain terms regarding the dynamic response of measuring system. Now, dynamic response can also be further classified. For further classification, one is time response, another is frequency response. Now, time response of the instrument. So, for time response of the dynamic system, there are certain differential equations for input and output. We will discuss those equations in subsequent slides. There are equations for input and output, and solution of these equations has to be attained in order to find the time response of dynamic system, and it has two parts: transient and steady state. Transient and steady state. Transient means it is time dependent. Now, steady state response of the system is not dependent upon time. It is dependent on input quantity. So, there are two parts of time response of dynamic systems. Another is frequency response of dynamic system. So again, we will have a frequency response system, frequency response function. And in frequency response, there are two things. One is change in amplitude, right? And another is change in the phase angle. In frequency response, the frequency is not altered. If input is 50 hertz, the output will be of the 50 hertz. There is a possibility, or it normally happens, that amplitude may change, amplitude of the signal may change, or the phase angle may change, or phase angles often changes. So these two things are change in frequency response of frequency dynamic response of measuring system. And the benefit of this type of analysis is we can divide system in a number of components. And we can have dynamic response of each component, and then we can integrate and we can find the response of the measuring system in totality. For this also I will give example later on. We will start with the generalized mathematical model of measuring system. And generalized mathematical model starts with, suppose output is, we will start with the output an dn qo by dt n plus a n minus 1 d n minus 1 qo by dt n minus 1 and so on. And when we get a1 dqo by dt, right? And then AO QO. This is a generalized linear equation for differential equation for output. And for input also, we can take as bn d raised to power n qi ttn plus bn minus 1 d to power n minus 1 qi dt n minus 1 b. This is A1. So B1 d qi by dt plus bo qi. This is a very generalized type of equation. And for time-dependent analysis, we have to solve this equation. And these parameters are constants. They are all constants. Now, this equation can further be written in the form of D operator, because if we say we can have solution of this equation by two methods. One is D operator method, another is the Laplace transformation, right? But here we will adopt the classical method of solving these differential equations. So if I write this equation in the form of D operator, then it is going to be an dn plus a n minus 1 d n minus 1. It is will go to a1 d plus ao q qo is equal to again bn then dn plus bn minus 1 dn minus 1 plus b1 d plus bo qi. Right? Now, this solution of output, we'll start with the output. We'll take them one by one. We'll start with output. So, output QO output. The solution of this equation will have two terms. These two terms are QO complementary function and QO particular integral. Fine. Now, this complementary function will be a function of time, is necessary a function of time. And it has n arbitrary constants. It has n arbitrary constants. And these constants, the value of these constants can be evaluated by imposing initial conditions. So we'll keep on imposing the initial conditions. We'll get the value of all arbitrary constant of complementary function. Particular integral does not have any arbitrary constant. So we'll start with complementary function, right? And when we start the complementary function, we can take as this equation, this one can be taken as 0, or we can say that a n d raised to power n plus a n minus 1 d raised to power n minus 1 up to a1d plus ao is equal to 0. We'll rub this off. Now, for this differential equation, we can have roots which are real and they are not equal. I mean, we have to take different combination of real and unreal and complex roots, right? So we'll start with the first one. The roots are real and they are unrepeated. Sorry, not equal. I said not equal, it is unrepeated. So real roots unrepeated. When roots are real and they are unrepeated, then solution is C e to power st, when s is the root. For example, the equation has this nth order equation. Suppose equation has 3 roots, minus 1.5, plus 2.5 and 0. In that case, the solution is going to be C1 e raised to power minus 1.5 t plus C2 raised to power 2.5 t plus C3, because it is 0. So this is the solution. Now imposing initial conditions, we can find the value of C1, C2 and C3. That is one case. Now suppose the roots are real and they are repeated. Repeated means we are having roots like this, minus 1, again minus 1, let us say plus 2, again plus 2, and let us say 0. So minus 1 and plus 2 are repeated. In the repeated root, when the roots are repeated, the solution is CO plus C1t plus C2t square and so on up to, let us say, they are p times repeated, so C p minus 1 and t raised to power p minus 1, because we have taken 0. So pth term is going to be Cp minus 1. Right, and this is multiplied by e raised to power st. Now considering this configuration, we can have roots in this case is as CO plus C1t, right? Because it is repeated 2 times. T is equal to 2. If it is repeated 3 times, then we will go for second order of t. E raised to power minus t plus C2. This is not this C2. This is different C2. C2 plus C3t e raised to power 2t plus C4, right? So we can have this type of, or suppose this 2 is 3 times, then C3 plus C4 t square, something like that. And suppose 0 is repeated 2 times. This 0 is repeated 2 times. Then it is going to be C4 plus C5t. Likewise, we can have solution when there is the roots are, real and repeated. Now, roots can be complex root also. When the roots are complex, and unrepeated. Complex means a plus ib. This is complex, right? And I is equal to plus minus under root a minus 1. So when the roots are complex and unrepeated, thus, and they are in pair, plus minus a plus ib. So when the roots are complex and unrepeated, the solution is c e raised to power at sine bt plus phi. Phi is the phase angle, phase change in phase. So for example, I will take one example here. Suppose the roots are minus 2 plus minus 4i, that is there, and then 3 plus minus 5i, and 0 plus minus 7i. The roots are like this. Now when the roots are like this, then we are going to have the solution as CO e raised to power a. Here the value of a is minus 2. So minus 2t sine bt. B is 4. bt plus phi 1, or let us say phi o. Some phi. We don't have the value of phi. And then it is going to be, next one is C1 e raised to power 3t. Similarly, sine 5t plus phi 2. So here we can make, instead of b value is given, so it is 4t. Now 0, here a, the value of a is 0, so it is going to be equal to C2 sine 70 plus phi 3. And so on, we can find the solution of the roots. Now again, we can have complex and repeated also. The roots are complex and repeated. When the roots are complex and repeated, in this case, the solution is going to be Cu e raised to power at sine bt plus phi o plus C1 t e raised to power at sine bt plus phi 1, and so on. So here the phi is changing and this component of t is added. Now here also we can take one example. The roots are let us say minus 3 plus minus 2i. That is one root. Again minus 3 plus minus 2i, right? And next one, let us take 3 plus minus 2i. So these roots are repeated. So in order to express these roots, it is going to be CO e raised to power a is here minus 3. So minus 3t sine b is 2t plus 5. Now it is repeated. Since it is repeated, then we will take C1t again e raised to power minus 3t sine 2t plus phi 1. Okay, and this is single, it is not repeated. So this is going to be C2, C0, C1, C2, e raised to power 3t sine 2t plus phi 2 like this. So we can address all type of roots. If the roots are real, repeated, unrepeated. If the roots are, complex, in that case also repeated and unrepeated roots are addressed in this case. So this is about complementary function. QO, complementary function. Now we have to find the particular integral also in order to have the total solution of this differential equation. QO PI. And QO PI, there is no universal method to find QO PI. The reason being that this particular integral will depend upon the nature of input signal. It will entirely depend upon the nature of input signal. So there is no universal method to find the particular integral. That is first thing. And input function, if it is a function of primary engineering interest, then we can have certain value of particular. Suppose function is sinusoidal function or input function is a step function. So then in those cases, the functions which are of engineering interest, we can find the value of particular integral of output. So there is no generalized method of finding out the solution for particular integral for the output. There is a method of undetermined coefficient. This method can be used for finding out the solution for particular integral for the output. Now, the method of undetermined coefficient, again we will have to ask certain questions in this method. The first is, if after certain order of derivatives, higher order of derivatives, are they zero? First of all, higher order derivatives are zero after a certain order of derivatives. Second thing is, the higher order functions have same functional form as lower order functions. That is also possible, that higher order functions have same functional form as the lower order derivatives. And the third is, the functional form is continuous and it is rising. If functional form is continuous and rising, then this method of undetermined coefficient is not applicable. But in the previous two cases, when it is higher order is zero, the functional the higher order derivatives are zero, and the second one is the higher order derivatives have functional form as the lower order derivatives. In those cases, we can find the solution of particular integral with the help of undetermined coefficients. And in that case, the solution of particular integral is going to be AFT plus B F dash T plus C F double dash T. It will be in this form. If it is given, it will be in this form. Now, after this, we'll come to a very important parameter in dynamic analysis of measuring system, that is operational transfer functions. Because in subsequent lectures or subsequent analysis of dynamic measuring systems, we will be frequently using this term, operational transfer functions. Now, operational transfer function it is depicted by QO by QI, and this is equal to, right, BM dm plus BM minus 1 dm minus 1 and so on, QO by QI. And this is B1D plus BO divided by input. Input is AN d raised to power n plus AN minus 1 d to the power n minus 1 plus AOD plus. This is different from the output input ratio. Output input ratio is instantaneous, and this is a function. This is a function which shows the relationship of output with input. It is entirely different from output input ratio. So this operation function, transfer function, shall be used in future analysis of dynamic systems. And this operation function is very helpful. Suppose I'll give you an example. Suppose I want to measure output of certain transducer. There is a transducer. I want to measure there is some input QI, and I want to measure certain output. The output of the transducer is in volts, and it has some transfer function. Let us say it is KT, transfer function KT for transducer. Now transducer output signals are very low, so they often go to the amplifier. So when it is going to the amplifier, again amplifier has certain transfer function, and it is again giving voltage but higher voltage. It is amplifying the voltage, right? And then it is going to a recorder. There is a mechanical recorder where on a paper the input is traced. So there is a recorder and it has transfer function KR, and output is displacement, movement of the pan or displacement, right? So movement of the pan is related with QI. Now we have transfer functions. So we can simply say X by QI is equal to the transfer function is going to be, in this case, because output of this is input of this. So transfer function is going to be product of this, this and this. So this is how a complicated system can be divided into small components, right? And these components, simply the transfer function of these components is multiplied to get the final output and input relationship. Okay, so that is operational transfer function. We'll discuss in details in operational transfer function when we'll go for the further analysis of dynamic response of measuring systems. Now, there is a sign input also, frequency input. This is a linear input, time domain input, another is frequency domain input. So when there is a frequency domain input, the frequency domain has also transfer function, that is QO by QI, and it is denoted by I omega. Omega is frequency 2 pi n, right? And is equal to, again, BO I omega, sorry, this is Bn I omega n plus B, this is M, Bm minus 1 I omega m minus 1 and so on, and it is B1 I omega plus BO divided by input, that is An I omega, this is M, n plus A n minus 1 I omega n minus 1 and so on, and then B1 A1 I omega plus AO. So this is how a transfer function is expressed for sinusoidal input. So because when we come across the measurements, there are, many instances when we have sinusoidal input to the instrument. Now response, suppose there is a sine input to the instrument. There is an instrument and it has to measure sine waves. The response of the instrument may be like this, that initially some dynamic response, but later on the output will stabilize. Right? So all these responses of the system, dynamic responses of the system under the sinusoidal input also we will be discussing in the subsequent lecture. So this is the introduction of dynamic response of measuring system, and from the next lecture we will start taking particular cases for dynamic response of measuring system. That is all for today. Thank you very much.